Section 4. Minimum variance hedge. For a number of reasons mentioned earlier, the final basis in a hedge is a random quantity, and this precludes the possibility of a perfect hedge. One common method of hedging in the presence of basis risk is the minimum variance hedge. Minimum variance hedge provides a formula for the hedge ratio. That is, the ratio of the size of the position taken in the futures contract to the size of the exposure. We're going to see that if the objective of the hedger is to minimize risk, setting the hedge ratio equal to 1 is not necessarily optimal. Suppose at time t1, we have an obligation to purchase W units of an asset at time t2. Thus, the cash flow to occur at time t2 is W times the spot price of the asset at time t2, which we denoted by X. Suppose F is the futures price of the contract that is used as a hedge, and H denotes the size of long positions taken of the futures contract. Note that the size is in the units of the underlying asset. Denote the hedge ratio by beta, then we have beta equals to H divided by W. Neglect interest payments on margin accounts by assuming that all losses or profits in the futures contracts are settled at time t2. Then, the hedged cash flow at time t2, denoted by Y, consists of two parts: the original obligation, that is W times S2, and the losses or profits in the futures account, that is the difference between the futures price at time t1 and t2 times the size H. Substituting the hedge ratio beta, we have this alternative expression for Y. At time t1, both S2 and F2 are random variables. Thus, Y is also a random variable, and we can calculate its variance. Note that at time t1, F1 is a known constant, and we can ignore it. And taking out the deterministic coefficient W, we only need to focus on the variance of S2 minus F2 times beta. By definition, variance is the expectation of the square deviation of the random variable from its mean. Here we use S2 bar and F2 bar to denote the mean of S2 and F2 respectively. Rearranging the terms, we get the following expression. And expand out the square, we have the expectation of S2 minus S2 bar square is equal to the variance of S2. The expectation of F2 minus F2 bar times beta square is equal to beta square times the variance of F2. And the expectation of the cross product term is nothing but negative 2 beta times the covariance between S2 and F2. This variance can be minimized by setting its first-order derivative with respect to beta to 0. That is, beta solved from the following equation minimizes the variance of Y. Therefore, we obtain the minimum variance hedge ratio, which is equal to the covariance between S2 and F2 divided by the variance of F2, and we denote it by beta star. Hence, the optimal hedge size, denoted by H star, can be calculated by W times beta star. Let ρ denote the correlation coefficient between S2 and F2. Then, beta star can be rewritten as ρ times the ratio of the standard deviations of S2 and F2. Furthermore, by substituting the optimal beta to the expression of the variance of Y, we get the following optimal variance of the hedged cash flow. This can be alternatively expressed in terms of X and F2, where X is the cash flow of the original obligation without hedge. Note that, since the ratio of the square of the covariance between X and F2 and variance of F2 is positive, we conclude that the variance of Y is less than the variance of X. That is, the hedge reduces the variance of the cash flow and hence the risk. The effectiveness of the hedge can be measured by the ratio of variance of Y and variance of X, or that of the standard deviation of Y and standard deviation of X. By the second expression of the optimal variance of y given in the previous slide, we can easily get that the ratio of variance of y and variance of x is equal to 1 minus the square of the correlation coefficient between S2 and F2. As a special case, suppose that the underlying asset of the futures used for hedging is identical to the asset in obligation, and there's no mismatch in maturity. Then we have F2 equals S2, and hence the covariance between S2 and F2 equals the variance of F2. And therefore, the minimum variance hedge ratio beta star is equal to 1. In other words, the minimum variance hedge reduces to the perfect hedge when the futures price is perfectly correlated with the spot price of the commodity being hedged. Now let's take a look at an example. The Big H Corporation, a US company, has obtained a large order from a Danish firm. Payment will be in 60 days in the amount of 1 million Danish kroner, DKK for short. Big H would like to hedge the exchange risk, but there's no futures contract for DKK. The chief financial officer at Big H decides that the company can hedge with Swedish krona, SEK for short. Although SEK and DKK do not follow each other exactly, they are highly correlated. He notes that the current exchange rates are $0.15 per 1 DKK and $0.12 per 1 SEK. Hence, the exchange rate between SEK and DKK is 1.25 SEK per 1 DKK. Therefore, the receipt of 1 million DKK is equivalent to the receipt of 1.25 million SEK at the current exchange rate. He deduces that he needs to have a short hedge on 1.25 million SEK. Given that the monthly fluctuations in the US exchange rates for DKK and SEK have a correlation coefficient of 0.8, the standard deviation of these fluctuations is 4.5% of DKK USD and 4% of SEK USD. Then, the minimum variance hedge strategy will suggest the following optimal hedge ratio. By the formula we derived earlier, the optimal beta is equal to the ratio of the covariance between the exchange rates of DKK USD and SEK USD and the variance of the exchange rate of SEK USD. This is equivalent to the correlation coefficient of the two exchange rates times the ratio of the standard deviations of the two exchange rates. Substituting in the figures given, we get the optimal beta, which is equal to 0.9 times the exchange rate of DKK SEK. Thus, the minimum variance hedge size for 1 million DKK is 1.125 million SEK, which is only 90% of what suggests by a full hedge based on the exchange rate. In the next lesson, we're going to see how the minimum variance hedge strategy is applied for hedge and equity portfolio using stock index futures.